Welcome to the latest in our series of talks about programming languages. I want to start out, as I do every week, by making a pitch for anybody who knows anything about programming languages that they think that other people might be interested in, to come talk to me and give a talk. Talk to me and we can set up a talk. My name is Jeremy Manson. My email address is jeremymanson@google.com. It's really easy to find. This week, by popular demand from people offsite, we are going to be able to submit questions if you are offsite. So for all of those of you who are offsite, if you go to the website qdb/questions/878, you can submit your questions. Today we have with us a speaker, Adam Langley, who is another Googler who is interested in giving a talk. He's going to talk about software transactional memory, which is a very important topic now. There are a lot of important...
Right, so the implementation for when you aren't using green threads and you really do have real threads coming around and stomping you.
Initiatives from companies like Sun and Microsoft and IBM and Intel about getting transactional memory off the ground. It's part of a broader effort, I think, in the whole programming languages community to get a better story for efficient and effective concurrent programming. And in the coming month or so, we're going to have a lot of talks on concurrent programming, including one by myself. So without further ado, I'd like to present Adam Langley and thank him for giving the talk.
Right, thank you. I'm not sure how well that video camera is going to work because I have a tendency to pace around when I give talks. So software and transactional memory. I understand this is going to be the first of a few talks on this topic. I can't profess to be an expert in it, but I do use it in real code in Google, and it works. So let me start off by presenting a dichotomy of concurrent programming. On the one hand, we have shared state programming, where different actors, threads in the shared state world, live in the same address space, they use the same memory, and they communicate by mutating that memory. Now, clearly they need some mechanism to stop standing on each other's toes, and traditionally that mechanism has been locks. So shared memory locks accounts for the vast majority of concurrent programming at the moment. Software transactional memory is another method for making shared state programming work. Now, the other side of the dichotomy is message passing concurrency, which at the moment is being championed by languages like Erlang. For those who don't know, Erlang is a language developed by Ericsson for programming telecommunication switches. And their big headline, the fact that everybody comes up about with Erlang, is that these telecommunication switches achieve something like 31 milliseconds of downtime per year on average. So clearly, message passing concurrency has something to go for it. And recently, on a few programming language weblogs and such, people have been saying that software and transactional memory, we shouldn't approach it, we shouldn't use it, because what we should really be doing is shifting to message passing concurrency. And this is just giving legs to a dead idea. Shared state concurrency is bad. We should abandon this because it's helping it along. I actually think this works really, really well. So maybe in the long term, message passing concurrency is the correct thing to do. But for the moment, this is pretty awesome. So let's have a look. Right. So everybody might want to take a moment to remember a time when every single one of these problems has bitten them. So this is the problems with locking. You can take too few locks, you can take too many locks, you can take the wrong locks, you can take the locks, but in the wrong order. You can leave the world in an incorrect state when something odd happens, or you can lose wake-ups and your threads can hang around forever waiting for an event which will never come. So if you haven't hit every one of these at some point in your career, you either haven't done a lot of multi-threaded programming or you're Mike Burrows. Personally, I am not competent to do multi-threaded programming because I have hit every one of these. I don't hit them terribly often, but when they do come up, they take me sometimes days to fix. So, I mean, locking is clearly an issue. Locks can even bite you when you don't even have any locks in your programs because somebody else is making a callback on a different thread. So, what's the alternative? Well, the alternative I'm presenting is transactional memory. Transactional memory involves recording the actions you're going to do and committing them. I mean, it's a concept that has been around in the database world for years. It's nothing new. So, how do we do that in programs? So, obviously, if there's only one thread in the world, it's not a problem. You can record your actions, you can perform them at the end, nothing can have interrupted you, nothing can have gone wrong. It's the trivial case. But what if somebody else comes along and mutates something that you're working on? So let's say you read a couple of values and you write a value. So if another thread comes along and updates one of the values after you've read it, but before you've committed the transaction, what can you do? Well, the only thing you can do is to abandon the transaction and retry it, which is a little uncomfortable if you're a programmer, right? It means that the block of code, which consists of your transactions, can be executed an arbitrary number of times, just magically. You have no idea. Maybe it goes once, maybe it goes 100 times. So obviously, you need to think about that. I/O inside a transaction is clearly problematic. So if you printed something inside your transaction and it retries, it will get printed every single retry. A couple of groups who I think will be presenting have some solutions for this, in which they buffer the output or roll back the input that you've read in the transaction. But the transactional memory that I'm going to be talking about today is based on the one in Haskell, specifically GHC's implementation. So Haskell is a pure functional programming language. And one of the things about that is in the pure functional programming language, your I/O is done using monads. Now, I'm not going to explain monads, nor am I going to use the Haskell syntax during this talk. Because I know that that will take some time. I mean, not that that wouldn't be a wonderful talk. It would be, and it should probably happen at some point, but it's not this one. So I've made up a syntax which is vaguely C-like, so people know what's going on. And monads, for this talk, you can consider as a contagion in the type system. So normally, your getChar function will return a char, obviously. But imagine for the moment that any non-deterministic or side-effectful function, in fact, returns its value wrapped up in an I/O. So an I/O is a magic thing which says this function depends on something other than its arguments. And if you call a function which returns an I/O, you return an I/O, and so forth. And so any non-deterministic or side-effectful function contagions up the call stack, and the type system marks everything as I/O. Now, this means that we know what functions are going to do I/O, so we can exclude them from the middle of our transactions. This is why transactional memory works so well in Haskell. Let's move on. What am I saying next? OK. So along with I/O, I'm also going to introduce another type system contagion called STM. So STM is the monad for things which do transactional memory operations. So you can compose STM operations with other STM operations, and you can compose them all the way up. You cannot have any I/O in an STM operation. And when you finish composing your transaction, you turn it into an I/O operation and execute it. Because if you're doing something which can affect other threads, that is I/O. It may not be reading or writing to a socket, but it makes the function non-deterministic in that another thread can come along and affect it. So this is a very simple example. This is decrementing a counter. So it's obvious, right? You read the counter, you write the counter. Now, that isn't a transaction. That's just a function that you can compose together into other transactions. Next one. So, sequential composition. Now, we can do atomic decrements with weight-free algorithms. There's an atomic decrement call in the Google 3 code. There's a lot of weight-free algorithms in the Java standard libraries. Do I need to explain weight-free, lock-free? No? OK, people are shaking their heads. Maybe in a sentence. So weight-free means that the system always makes progress. It can never deadlock. And every single actor in the system proceeds in a bounded number of steps. Lock-free is the same thing, except that actors can be starved. This software transactional memory is only lock-free. I'll come back to that when I talk about implementations. So there are lock-free hash tables in Java, and you can use them and they work great, but you can't compose them. You can't atomically take an object out of a hash table and put it into another. Just as in Google 3, you can't atomically decrement two numbers using just the atomic decrement function. But here we are composing two decrements, and we are wrapping it in a call to atomically. So atomically, we'll take that transaction and run it, and it will happen atomically, and everything will just work.
doesn't that depend on an axiom that there are no other threads that are accessing counter or counter 2 which are not using the IO STM primitives?
Sorry, so if another thread was accessing it at the same time,
They just counter 2.
yeah, so what would happen would be that we would abort this transaction and retry it. So when it came to the end of the transaction, we would check everything we've read. We would make sure that we saw a consistent state of the universe. And if we had, then we atomically commit this.
But if the process or thread accessing counter 2 is using Google 3 and not STM, then you're screwed, right?
Yes.
Okay, that's all I just wanted.
Oh, absolutely.
Questions where necessary.
Repeat the questions. Everybody told me this when I came up, and I'm still forgetting.
In other words, these primitives work as long as everybody in the world uses the same primitives.
Yes, absolutely. So in Haskell, this works because anything which uses an STM primitive gets wrapped up in that STM monad, and it contagious up the type system, so you know. But yes, you're absolutely correct. This doesn't work if other threads in your system are doing wild, crazy things. So STM is, you either partition your concurrency into an STM and non-STM part, or it's everything. But even so, this is clearly quite a bit better than locks, because in locking, you would need to find everywhere which uses counter, everywhere which uses counter 2, and everywhere which might need to impose some, some ordering on accessing between them. And of course, you need to take those locks in the right order. So that's quite neat, but we can do better. So this is how STM handles events. So in locks, you'd use condition variables, or if you're on Google 3, you can use the await and lock when. But in this will block if v equals 0. And the way it does this is when it hits retry, it will look at the list of every variable it's read and wait on those variables. So all the STM variables have wait queues hanging off them. And when a transaction completes, it will wake up all of the threads which are waiting on the variables which have just been written. So another transaction comes through and it sets v to 1. If this has called retry, this will get woken up, it'll abort its transaction, it will retry, and it will run through, and now it will be able to complete because v will be equal to 1. And this means that you can't lose wake-up calls. You can do retries arbitrarily deep. And this is a fairly specific part of the GHC implementation of software transactional memory. Not all software transactional memory support this. But once again, it's just a very neat trick. And we get better. Sorry?
I'm sorry, I don't, what does it get you? I don't understand it at all.
Right, I'm clearly not explaining myself correctly. So imagine that we were writing lock-based code. And we wanted to wait until this was non-zero and then decrement it. So we would have clearly a lock around counter. We would have a condition variable. And everybody who used counter would have to lock it. And if they've incremented it, they would have to fire the condition variable and so on and so forth. And you'd have to wait in the while loop, checking the condition variable is non-zero, and then decrementing it when it was correct. So what this gets you is that you don't have to bother with any of this stuff. You can throw away your condition variables. You don't have to worry that maybe somebody isn't using the condition variable elsewhere in the code, and so your wake-up call will never happen.
What are the semantics of the retry? What does it do?
Right, so as I went through before, retry looks at all of the variables you've read, and it hangs the current thread on a wait queue of all of them. So at this point, we will have read counter, and if it's 0, we hit retry. And retry will suspend the current thread until counter, in this case, has been updated. Now, it may not have been updated such that it's non-zero. It may have gone to -1. But anyway, this will be woken up when retry happens. So you can consider retry as just aborting the current transaction and trying again. And the fact that it's waiting is just an optimization. It could busy wait, right? And the semantics would be the same. But as an optimization, we look at the things we've read. Therefore, those are the only things which can affect us because we're deterministic. There's no I/O. And when they've changed, it's worth considering whether we can complete again.
I guess another way of phrasing the same question, which
I forgot to repeat.
when did the transaction start? Let's say you have a retry nested deeply inside several functions.
Yeah.
How does it know where to retry from?
So it retries from the top of the transaction.
Well, I don't see the top of the transaction in your code here.
Right. So that's because if we made this a transaction, we wouldn't be able to compose it with any other functions. So a transaction is made with the atomically call. So you can see their det counter are in the STM monad. Maybe I should have explained monads. But you make a transaction by calling atomically on it. And so a retry, no matter how deep it is, will run all the way back up to the start of the atomically block.
Okay. And presumably those are nested too. Like if you had an atomically thing which called another one which had an atomically in it, if either one had to do a retry, it sounds like there might be some sort of scoping. It would retry to the top of the transaction that's on the top of the nested stack.
So in this particular case, you can't nest atomicallys. So if you have an atomically, you'll notice det counters returns an IO type, whereas you can't have an IO inside a transaction. So if you had an atomically inside one of this det counter, then you wouldn't be able to nest it because the type system wouldn't let you. But in other STMs, certainly you can. Other STMs don't enforce that, and you're right, they have their own semantics for nesting.
So if you can't nest it, then let's say I want to use the standard hash table, which does little locking on its own, and I want to make a transaction which involves reading and writing a hash table. That means it's impossible.
So if the hash table, if it exports a function which has a transaction inside it, yes, you cannot compose them in Haskell. So what it needs to export is, rather than something that's wrapped with atomically, it needs to just export it without the atomically around it. And then you can compose it together, and then you can put your own atomically around it when you're done.
Adam, somebody from Kirkland says, repeat the questions, please.
Repeat the questions, please. So I didn't repeat that one because I thought my answer explained everything.
Well, sometimes.
Right, yes.
I wanted to add that there is actually a lot of, on top of the previous question, there's a lot of research on how to nest atomic blocks correctly. All the semantics of that should be exact. So it's nice that this is a little bit simpler.
So yes, Jeremy was just saying there's a lot of research into how to do this. In this particular case, in Haskell, you can't do it. You have to compose everything before you call atomically. So, right, once again, this isn't a transaction. You'll notice this returns an STM type, so this can be composed. Now, what this is doing, this is a kind of nested transaction. So I've made up some syntax here. It's called or else. What this will do is this will try the first det counter or wait, and if it calls retry, it will try the second one. If that calls retry, then it will wait on the union of all the variables which they have read. So this allows us to compose blocking actions. Now, consider for a moment what this would look like if we were using locks. So if we were using locks, we'd have a function which can block, and we'd have another function which can block. So how would we do this? We would have to spawn off, I think, unless someone has a better design, we'd have to spawn off a thread to wait on each of these, which we then share a condition variable with, and then each of these threads can tell us when one or the other has completed, except that they could both complete at the same time, so the two threads would need to share a lock to make sure that only one of them signaled the condition variable. I mean, it's certainly doable, but in C++, it's going to be 100 lines of code, perhaps. So there you are. This is composing blocking actions, and basically, I'm just going through like the sparkly, shiny jewels of software transactional memory, and this is one of them. Any questions on what that means?
I don't understand when the or else is taken.
So the or else happens if the first part calls retry. So retry would normally block a transaction for something to be ready. But if it blocks, then it will try the second one. If that blocks as well, then the whole thing blocks, and it waits on the union of all the variables that have been read. So if either of these counters are then updated, the whole transaction starts again, and it will try the first one, and then the second one, and if they both block, it will wait again, and so forth. And I'd just like to point out that I've just made up this syntax. Clearly, if you wanted to test 3 or 4 counters, you would start indenting across the page. The actual Haskell syntax for that would be something along the lines of that. So I'm just saying, ignore my syntax, just think of the semantics. Sure.
In the previous example, if 2 threads were executing that same atomically example where you're trying to get the 2 counters, because of the way it's written, the order in which either one of these threads might acquire one of the counters is random because of the or else. So doesn't that lead to a potential deadlock between the 2 threads? Because it seems like one of them could get counter 1, the other one could get counter 2, now you're dead.
Right, so the question was, isn't there a possibility of deadlock if 2 transactions are going through the previous function and they acquire the counters in a different order? So the answer is no, because semantically the software transactional memory says that deadlock can't happen. And the reason it does that is because when the transaction comes to committing, it acquires the locks in some global total order, which is usually defined to be the address of the locks. So when the transaction came to commit, it would look at all the things it's read, and it would go, I need to lock this, this, and this, and it would lock them in the order of memory. And if another thread is coming along at the same time, then you need code to handle that. I'll go into that at the end. So yes, as I said before, this software transactional memory is defined to be lock-free, which means the system as a whole always makes progress, even though one particular actor may be starved. How am I doing for time? I'm going to...
You have 35 minutes.
Okay. So as I said, I'm just going through sparkly jewels of things you can do with transactional memory, and this is another one. This, I think, is unique to the GHC implementation. But what it allows you to do is it allows you to enforce invariance on your transactional variables. So here we make a transactional variable, and we initialize it with 0. And we have a check block, which is a transaction. And this check block is evaluated every time any of the transactional variables it reads is changed. So in this case, this function makes a transactional variable and returns it. It also puts into the global world this check function, which every time any transaction modifies this transactional variable will make sure it's less than some limit. And so this will allow you to catch, as soon as a transaction completes, any buggy transaction which is breaking your invariance. Once again, I mean, it's not fundamental, it's just very nice.
What will it do if the check is that the invariant is not satisfied?
So the question was, what happens if the invariant is broken? I mean, that's up to the implementation, clearly, but it will, I believe GHC will throw an exception at the point of the transaction which broke it.
Okay, so it can stop the program.
Yes, it's a debugging aid, and so it will shout and scream in some way that this transaction is buggy, you've broken your invariant. These invariants can also be defined based on the difference of the old value and the new value. So here we can check that the transactional variable we're returning is always monotonically increasing. In fact, strictly monotonically increasing. Yes, it's greater than. Once again, as I said, just a nice trick. Right, graphs, as ever. So these graphs are from the Haskell implementation, and what was it? Oh, it was the array blocking queue example, which I'll come to. But the actual values in these graphs aren't important. All I want you to take away from this is software and transactional memory doesn't suck hugely. So on a uniprocessor, it's kind of roughly the same-ish, sure. When we give it 4 processors, it happens in this example that, so this here is increasing time. Increasing time is bad. This here is locking, and this is transactional memory. So this graph shows that transactional memory is actually beating locks in this particular example. But I don't want you to think that transactional memory is faster than locks, because you can equally come up with another example where the graph is inverted. The only thing I want you to take away from this is transactional memory doesn't suck hugely, in that it's perfectly reasonable to want to use it, and you shouldn't expect your performance to go through the floor. Okay, in fact, I'm going to go back that slide. I don't want to go onto that example yet. So I'm just going to discuss GHC's implementation a little of transactional memory. So in GHC 6.4, they're 6.6 now, which is fully multi-threaded, but in 6.4, they were in fact only green-threaded, which means the kernel thought the process was only one thread, and the thread did the scheduling inside of itself. So this makes transactional memory kind of easy, right? Because whenever you're in the C runtime, there is only one thread executing. So the way GHC works, and I'll come to another implementation later on, is whenever a thread starts an atomic block, it makes up a transaction descriptor which contains a list of all the variables which have been read and all the variables which have been written. And as the transaction progresses, obviously things are added to these descriptors. If you hit an or else block, then it nests the transaction, because if an or else switches to its alternative path, then you want all the things which the first path has done to be reversed. And there are a couple of little niggles in this implementation. One thing is that any given transaction may see an inconsistent view of memory. And so this can cause it either to throw an exception, or it can cause it to non-terminate. So you can imagine a for loop which starts off perfectly validly, and then its condition is decremented before its initial value at some point during the transaction. It will never terminate. So one thing GHC does is every time it schedules a thread which is in a transaction, it verifies the transaction is still valid. Valid means that all of the values it's read still have the same value as when it read them. And so if a thread is non-terminating because it's seen an inconsistent view of memory, it will abort and try again. Likewise, if a thread throws an exception, then GHC also checks whether the transaction is still valid, because the exception may have been thrown because it saw random contents of memory. If that's the case, the exception is squashed and it starts the transaction again. Look at my notes. What else do I have to say about this? I think that's it. Another thing to just point out is that the system must proceed globally, because the only way a transaction can be aborted is if another transaction has completed and stomped its variables. Therefore, something is proceeding right, because something is finishing transactions. However, a big transaction which runs for a long time may be constantly stomped by lots of little transactions coming through and breaking one of its variables, and the big transaction may retry in a loop. So we can starve big transactions, but the system as a whole must proceed, because the only way to cause a retry is for a transaction to have completed. So now I'm just going to quickly go through a less noddy example. This is an array blocking queue. It's used in Java. Java programmers should know what it is. It's basically a circular buffer of constant length, and it blocks when you want to add and it's full, and it blocks when you want to take an element and it's empty. So first off, we're going to define a fairly generic function which will be used to implement a couple of takes. It will be used to implement take, and it will be used to implement peek. So this function, first off, if you look at the very top left, it's an STM. So it's not a transaction in itself. It can be composed with other transactions. You want to not make things transactions as much as possible, because otherwise you can't compose them at a high level. But it returns an STM maybe int, which is either an int or it's a failure value. So what we're going to do, we read the number of used values in this array. If it's 0, then we're empty. And we have a couple of flags which tell us how we're acting. We have a flag called remove and a flag called block. If we're empty and we're blocking, then we retry, which will suspend this thread. The only variable we've read so far has been used, so this thread will be woken up whenever the used variable is changed in any way. And if it's changed and it's 0, then we certainly hope it goes to 1. And so then we'll be woken up and we get to retry again. If we're not blocking, then we return a special value which says there is nothing in here. If it isn't empty, then we read the head. We take the value from this array which the head tells us to take. If we're removing it, then we update this structure with a couple of writes. Obviously you increment the head, you say there's one less used, and we return it. So if we imagine we just wrap this in an atomically block, imagine this is a transaction. If we get to here and another thread has come through and it's stomped either our used, or it's stomped, if we're updating, the head and the used, then we will abort, we will throw away everything we've done, and we will do it again. Which as I started at the beginning, is fine because there's no I/O in this. So this function can magically be executed 10, 100 times. Eventually, we hope that we'll be able to make a complete run and no other thread will have stomped any of our values, and we finish. I haven't got the version with locks in here, but suffice it to say, it's quite a bit longer and not nearly as clearly correct. And so from that more generic function, we very quickly define take and peek. Take is simply the case where we remove the element and we block. Peek is simply the case where we don't remove the element and we don't block. What's next? Okay, this is a more interesting example. This is taking from the queue with a timeout. So first note, this is I/O. We have a timeout. We're dependent on the real world. This can't be composed with other STM actions. And that's why you see the atomically call in there. So we start off by making a timer, which is of a type which I've just made up called T-chan. But you can imagine T-chan is a transactional channel. You know how channels work. They block if you try to take it, and it's empty, and so forth. It's very much like the array blocking queue. So we start this timer, and then we have an or else. So initially, we try to read from the transactional channel. That will block until that timeout has happened. So we will go through, read the transactional channel, that calls retry to block, and so then we switch to the or else, which says that we try to read from this array blocking queue, true means blocking and remove. And if it's empty, that will block as well. So both paths of our or else are blocked, so the whole thing blocks, and it blocks on the union of the variables they've read. That union is the array blocking queue and this transactional channel connected to the timeout. So when either of those triggers, this transaction starts again, and depending on which one has triggered, one of these paths will work. And so that's timeouts in, I don't know, what is it, about 10 lines of code, maybe less. And it's timeouts which are clearly correct and which you can't get your locks in the wrong order, you can't lose stuff. So now I'm going to go on to another implementation. This is an implementation from the lock-free group at Cambridge, the original Cambridge, not this American upstart. And so has anybody got any questions on transactions in the high-level view which I've gone through before I dive into this?
Maybe I got this completely wrong, but since you can't nest things, I assume transaction had to get fairly large. If one kind of at the higher level.
Right.
And at the same time, you have a lot of big number of threads. It appears to me that the chance that any two interactions interfere is pretty high.
Okay.
And so kind of how well does this scale kind of with big transactions and
so
number of threads?
The question was, because transactions don't nest, your transactions are going to end up being fairly large, and doesn't that mean that they'll retry many times and thus progress will be slow? So transactions do kind of nest, right? Or else is a nesting of transactions in some sense, in that if one branch of an or else blocks, then it's undone, and the transaction carries on the other branch as if it had never happened. So they do nest in some sense in Haskell. Also, in other STM implementations, they may nest as much as you like. But the question of don't large transactions stomp each other and cause the whole system to proceed slowly? Possibly. As I said, I showed you that graph where STM beat locks. You can come up with other examples where locks beat STMs. In practice, what I've seen is that it works fairly well. Jeremy?
Also, it should be pointed out that you never have to have a transaction that's longer than you would otherwise lock.
Right. So Jeremy's saying you never have to have a transaction longer than you would otherwise lock, which is true, right?
Because it's whatever you're doing concurrently that you don't want to put in the real.
Yeah. And if your transactions do end up fairly large, you should probably question your design maybe a bit. Same way if your locks end up spanning a longer time. Okay. Any more questions before I dive into the crazy implementation? This is a linked list, and so you can see the cons cells in this linked list, rather than pointing to each other, in fact point to these hidden structures under the water. these hidden structures under the water are managed by the transactional memory. And this is a completely different transactional memory design than I've been speaking of before. And so let's just look at some code for how you would manipulate this. Right, isn't this fun? So you can see STM object is the type of an object which is protected by the transactional memory. And so the do here is the transactional memory loop, and it's explicit. So your code doesn't magically restart. The restart happens here. And so in this particular implementation, you have to do it all of yourself. I'm not going to go through this in great detail, but you can see that I got the laser pointer. You can see that the code pulls. It pulls from the transactional values. It pulls the real values out by calling open for reading, and there's a similar open for writing down here. So this is how you add transactional variables to your list of read objects and your list of written objects. And this happens to be a list insert, and this is fairly standard. You're walking along the lists to find the position where you should insert it to keep it ordered. And then this down here, commit transaction. If it returns false, then the transaction has aborted. You need to restart. So this is when the transaction is committing. So what we do, we have a read list, and we keep an idea of what we've read in this read list, and we have a write list. And so when we open an object for writing, we make a shallow copy of it. When we actually write to the object, we write to this shallow copy, and other transactions can go through and they see the old values. When we come to finally commit, we walk through and this pointer here, this is an STM object. Normally, this pointer here points to the real object. But when we come through to transact, we use an operation called compare and swap. Compare and swap is implemented in the processor. It takes 3 arguments. It takes a memory address, an old value, and a new value. And it atomically, using bus locking, says, if what's in the memory address is the old value, replace it with the new value, and tell me what ended up in the memory address. So this pointer here, we can atomically update when we commit to point to our transaction. And this is called the acquire phase. We go through and we update all of the things we've opened for writing to point to our transaction. Now, if another transaction comes through and it wants to do the same thing, it finds, let's think, at the end of the acquire phase, rather than finding that, it finds our transaction. And it can look up in our transaction the actual value of y it should be using. So another transaction comes through, finds that, points to there, and it finds our value of y and starts using that. Sure.
Is the definition of a transaction in this system, does it restrict itself to a single compare and swap, or can they be, can you have as a transaction something that will require some series of compare and swaps?
So the question is, can you have one object open for writing? No, you can have many objects open for writing. And when the transaction starts to commit, it will go through in a global total order, which, again, is generally the order of the memory addresses. And it will try to acquire all of them. If it finds that, if the compare and swap tells me that the value there wasn't what I expected, then the transaction is aborted. So we go through, in this case, we only have one write object, but we go through all of our write objects and we point them at our transaction. This means we now owe them. We then go through all of our read objects and we use compare and swap to make sure that the value in them is what we read when we first read them. If not, then another transaction has completed and we need to abort. Once we've owned all of our writes and we've checked all of our reads, we're ready to go. And we go through and we compare and swap and get rid of our transaction object and point this to what was our shallow copy, but is now the original version. And what we happen to have done in this case is we've removed an element from the end of the list. If another thread comes through and it notices that it has been tripped up by our transaction committing, then rather than abort itself immediately, what it will actually do is the other thread will call our commit function. So you can have multiple threads all committing the same transaction at the same time, but because they are using compare and swap and because they're working in the global total order, what it will actually do is it will help. One of them will always get there first. And that's what makes sure that we always have progress in the system as a whole. So another thread gets tripped up, it will help the first thread complete its transaction, and then it will abort itself. Now, every time I look through the pseudocode for this, I have to convince myself that it's actually correct. And I did it again this morning, and by this afternoon, I won't remember. So any questions on this are entirely welcome and completely reasonable.
2 points. It looks to me as if this system, which I rather like, could be transformed into an equivalent system if you replaced every open for write by a lock, and then when the callback to the transaction commit happened, you release the locks in case you didn't have all of it, roughly speaking. The second thing is...
Can I do one at a time?
Okay.
So the question was, can't this system be transformed into another where every open for write is converted into taking a lock for that variable? Well, let's think. Trivially, you can convert any software and transactional memory system into a big lock. And that's obviously correct. It's inefficient, but it's correct. But your transactions can still get stomped if somebody else has written one of the variables you've read. Or do you want to lock the read variables as well as the write variables?
I have to think about it.
Yes. So I can't answer right now whether it works. It possibly would. It's possibly another reasonable implementation. I'm not sure. Second part.
What about the ordering? If you lock in the order that...
Yes, the order could be different. That's a very good point.
Well, yeah, I understand, but remember what I said is that it's a locking system where you have a callback if somebody else has got some of the locks that you would like, and then you release your locks. So that's how you make progress, and that's actually equivalent from what I think I understand you explaining.
So you're saying, just for the people watching, that it's a callback system where locks can be released if they're contended on and taken in the wrong order. It sounds like you might have a reasonable implementation.
Because what you're really doing, you say, I pretend to take a lock, I pretend to take a lock,
Yeah.
I got all my locks, so now I'll commit. You could say, I take a lock, oops, I can't get this one, so I'll release all my other ones, right? Without actually having done any I/O or any updates.
Right. So it sounds like you want to implement software transactional memory.
No, I've done these things before.
Okay.
My second comment is that I've observed in systems like this can be unfair unless all of the players have equal latency to the compare and swap or whatever you're using for the underlying mechanism. If the system is bigger than 4, right, you will usually have hot spots and cold spots, and processes can get frozen out and not make progress because the other guys are getting faster access to the underlying mechanism, whether it's a lock or not.
So the second part of the question was, this system can be unfair if there's like latencies between different transactions. Yes, it absolutely can. Starvation can occur. This is only lock-free. The system as a whole makes progress, but large transactions can be consistently kicked out by smaller ones. Yes. One at the back there.
Well, for this suggestion, I think the big part for important is that in order to release locks after writes, you would have to, if you're doing this yourself, you would have to write configured rollbacks, right, to replace the values with the old values prior to your changes.
Yeah,
So
that's the magic that's inside the his commit transaction function. You write your own commit transaction function, then that has to have everything that you just said.
Well, but I mean, this is the hard part, right? Locking is easier, except for deadlock, which is the other part that this is presumably going to handle. But the hard part is doing all of the essentially compensating work to back out if you hit one of these. So I think this is the big win in the system, is doing all the pieces that, say, a database gives you in terms of rollback.
Right. I don't need to comment on that. Waldemar?
What does the memory model for this look like? I mean, for normal locking, lock doesn't acquire barrier, unlock does a release barrier. Where are the barriers here?
So the question is, what does the memory model look like? The memory model, of course, is defined by the implementation. I couldn't give you exact details on this, but in general, the memory model is, it works, right? It will be handled by the transaction system. You don't need to worry about it.
software transactional memories are not far along enough. I actually wrote a paper on this last year. Software transactional memories are not far along enough to be able to decide something really, really solid with respect to memory model. In general, it's got the same begin a transaction, fence, end a transaction, fence again property, but like the real details, they haven't quite worked out what the semantics should be enough to actually work out what the actual real details are of it yet.
Jeremy was just saying that they don't really have one and not far enough along in the research. Any more questions? Sure.
So you almost should call it roll your own transactional data structures rather than transactional memory, because this is all about data structures and how to lock them.
Yep.
So there are people at like places like Intel and Sun are actually working on hardware combination solutions.
Yeah. That's been tried before. The rollback is really tough when you're doing it in hardware.
Oh yeah. Repeat here again. If you repeat the place they can go online, it's qdb/questions/878.
So if you're watching, the place to go online is qdb/questions/878. Right. I think someone right at the back there?
Can you say a little something about what implementations are available? I mean, you mentioned Haskell. But...
Right. Can I say something about what implementations are available? So the third of these is the Lockfree group at Cambridge. They have an implementation which I just discussed at the end in C. The Haskell one is beautiful and documented at, well, the second one mostly. And there are certainly lots and lots of implementations, and some of these people might be coming here to talk about them. There is certainly a Java one, which I've seen. IBM have a group, right, Jeremy?
Maurice Hurley does one that's available for C#.
One for C#. SXM, is that?
Yeah.
Yes.
And there are a lot of them that are connected to that.
So I think it would be a Google search.
Tim Harris's.
Tim Harris's, yeah, he's Cambridge, right? Yeah.
That's available on Java.
So these are just the ones I've been talking about. There are lots. Okay. Right, are there no more questions? Thank you all for listening.